Welcome to Tell Me More Stories Told as podcast.
Great to be diving in.
Today, get ready because we're embarking on, well, an incredible journey. A deep dive into something absolutely vital, something you encounter with every single breath.
Oxygen.
Exactly. Oxygen.
And you know, this isn't just about a chemical element you find on the periodic table. It's really a story stretching back centuries.
A story filled with, curious observations, mistaken theories.
Oh, definitely mistaken theories. And brilliant breakthroughs, too. Think of it like a scientific detective story.
Okay, I like that. And we're here to piece together the fascinating puzzle of the air we breathe.
We are. We've got a stack of information from the earliest hints about air and fire right up to how we use oxygen today.
Right, so our mission, yours and mine, is to pull out the most captivating bits, the real nuggets, and lay them out in a way that'll, well, hopefully have you saying, tell me more.
Get ready for some aha moments, I think.
Let's start way back. Ancient times.
Well, maybe not that far, but let's go to the 2nd century BCE. Philo of Byzantium.
Philo, okay. What did he observe?
He noticed something pretty interesting. If you put a burning candle under a jar and put the mouth of the jar under water, the water level inside the jar rises as the candle burns out.
Okay, so he knew something was happening with the air.
Exactly. Now, his explanation wasn't quite right. He thought the air turned into fire and escaped, which isn't it. But it was a really early clue, that burning and air were somehow linked.
A crucial first step. Then we jump forward quite a bit.
We do. Leap forward to Leonardo da Vinci. He figured out that air wasn't just like hanging around during burning or breathing.
It was actively involved.
He was being used up, consumed in the process. Then, much later, late 17th century, you get Robert Boyle.
Boyle's Law Boyle.
That's the one. And he provided solid proof. Air is absolutely necessary for fire. No air, no fire.
Okay, so these early thinkers, they're circling it, getting closer. But the picture's still fuzzy.
Very fuzzy. But then comes John Mayo, an English chemist in the 1600s. He made a really significant leap.
Okay, Mayo. What was his contribution?
He proposed that it wasn't all of the air, but only a specific part of the air. He called it spiritus nitrarius.
Spiritus nitrarius. Catchy.
Yeah. He said this part was crucial for both fire and breathing, and his experiments were pretty ingenious for the time.
Tell me about them.
Well, he'd put, say, a mouse or a lit candle inside a sealed container over water, and he watched the water rise inside as the air got used up.
Just like Philo saw, but Mayo measured it.
Yes, and he observed that the water replaced about 1/14 of the air's volume before, the flame died or the mouse expired.
Grim, but effective. It strongly suggested this nitrarius was being consumed.
Precisely. And he didn't stop there. He noticed something else really important.
What was that?
When he heated antimony, it's a shiny metal, it actually got heavier.
Heavier? How does heating something make it heavier?
Unless it's combining with something from the air. He correctly reasoned that his nitrarius must be combining with the antimony.
That's brilliant. For the 1600s,
Yeah.
That's incredible insight.
It really was. He even had this idea way ahead of its time that our lungs pull this stuff into our blood.
And that's what powers us.
Essentially, yeah. He thought our body heat and muscle movement came from it reacting with substances inside us. His work, published in 1668, was remarkably close to our modern understanding.
So they were so close, they had this vital component identified, its role in burning, breathing, even combining with metals.
Yeah.
But then things went sideways.
You could say that. Science took a bit of a scenic route. Enter the age of phlogiston.
Phlogiston. I've heard of this, the theory that explained burning.
Supposedly, championed by Beecher, refined by Stahl, late 17th, early 18th century, it became the dominant theory.
So what was phlogiston, according to them?
It was this substance, this essence, supposedly present in anything that could burn. When something burned, it released its phlogiston.
Leaving behind ash, or what they called calx?
Exactly. So something like wood, which burns away almost completely, was thought to be super rich in phlogiston.
Whereas something like iron, which just rusts a bit, had very little.
That was the general idea. It seemed to explain why things appeared to lose mass when they burned, they were losing phlogiston.
But there was a big problem, wasn't there? Especially with Mayo's observation about metals getting heavier.
A huge problem, and they never actually isolated or measured phlogiston. Plus, the theory totally overlooked the active role of air. Air was just sort of there.
And the irony is, while everyone was focused on phlogiston.
People were actually making oxygen. Guys like Hooke, Borch, Lomonosov, Bain, several researchers produced it.
But they didn't know what they had.
Nope. Because the phlogiston theory was like wearing blinkers.
Yeah.
They couldn't interpret their results correctly. They just didn't have the right framework to understand that a part of the air was being added or was essential.
It's like finding gold but thinking it's just shiny rock because everyone's told you gold doesn't exist there.
That's a perfect analogy. Okay, so now we get to the actual discovery, and it's a bit messy, historically speaking.
Multiple claimants?
Yeah,
Intrigue.
you could say that. First, let's mention Michael Sendivogius, Polish alchemist, early 17th century, way before Scheele and Priestley.
Sendivogius.
Ah.
What's his claim?
Back in 1604, he wrote about something in the air he called cibus vitae.
Food of life. Sounds promising.
It does, and some historians argue persuasively this was oxygen. He also knew that heating potassium nitrate produced a gas, the same food of life gas.
And linked it to breathing.
Yes, linked it to the part of air essential for life. So there's a strong case he discovered it first, but
But he got overlooked. The unsung hero.
pretty much, his work wasn't widely recognized by the key players later on. A forgotten pioneer, perhaps.
Okay, fast forward to the 1770s. Now who's in the picture?
Carl Wilhelm Scheele in Sweden, a brilliant pharmacist and chemist.
What did he do?
Between 1771 and 72, he independently produced oxygen by heating various substances like mercuric oxide and nitrates. He called it fire air.
Fire air.
Yeah.
Apt. Because it supported fire so well.
Brilliantly well. He was meticulous, wrote a whole manuscript, Treatise on Air and Fire, in 1775. Problem was, it didn't get published until 1777.
Publication lag, the bane of researchers everywhere. And that delay was crucial, wasn't it?
It really was, because in the meantime,
Joseph Priestley enters the scene. August 1st, 1774. The famous experiment.
the very one, focused sunlight with a big lens onto mercuric oxide in a tube, watched a gas being released.
And this gas was
Well, Priestley called it dephlogisticated air.
dephlogisticated, meaning air without phlogiston.
Exactly. He thought he'd found air that was exceptionally pure, exceptionally good at absorbing phlogiston released during burning.
So he was still thinking in phlogiston terms.
Completely. But he was fascinated by its properties. Candles burned incredibly brightly in it.
And the mice.
Mice were more active, lived longer in it than in normal air. He even breathed some himself.
He breathed it. What'd he say?
Reported a feeling of lightness, ease in his chest, but again he saw it as super air, not a new element.
But he published first, in 1775, an account of further discoveries in air.
And that's why he often gets the primary credit for the discovery, because his work got out there first. Scheele discovered it earlier, but published later. Sendivogius possibly discovered it centuries earlier. It's complicated.
Science history is rarely neat. So Priestley discovers it but misinterprets it. Scheele discovers it but publishes late. Then comes the big name.
Antoine Lavoisier, the French chemist often called the father of modern chemistry.
And Priestley actually told Lavoisier about his findings.
He did. Priestley visited Paris in October 1774 and shared his experiments on dephlogisticated air. Apparently, Scheele had also written to Lavoisier about his fire air, though Lavoisier never admitted getting the letter.
Interesting. So Lavoisier hears about this special air.
And crucially, Lavoisier was obsessed with measurement. Quantitative experiments, that was his thing.
Not just observing, but weighing.
Precisely. His work on combustion, tracking weights meticulously, was revolutionary. Remember Mayo noticing antimony gained weight? Lavoisier measured it.
Like his experiment with heating tin in a sealed container.
Exactly, a classic. Heated tin, sealed it off. The total weight didn't change. But when he opened it, air rushed in.
Meaning some air inside had been used up.
And the weight gain of the tin perfectly matched the weight of the air that rushed back in. Proof.
Proof that burning wasn't about losing phlogiston, but about gaining something from the air.
That was the light bulb moment. It completely overturned the phlogiston theory.
And this led him to understand what air actually is.
Yes. In his big 1777 paper, Sur la combustion en général, he argued air is a mixture.
A mixture of.
What he called vital air, the part needed for burning and breathing, and azote, the part that wasn't, which we now call nitrogen.
And vital air became
Oxygen. He coined the name that same year, 1777, from the Greek oxys, meaning acid, and gens, meaning producer.
acid producer. Why acid?
Well, that was Lavoisier's one big mistake here. He believed incorrectly that oxygen was present in all acids.
Which it isn't. We know that now.
Right. Sir Humphrey Davy corrected that later. But the name oxygen stuck.
Did it catch on quickly?
Not immediately in English, funnily enough. Maybe some resistance, because Priestley, an Englishman, had made the initial discovery.
So how did oxygen win out?
Believe it or not, poetry helped. Erasmus Darwin, Charles Darwin's grandfather, wrote a popular poem called The Botanic Garden in 1791.
And he used the word oxygen.
He did, celebrating the gas. And that seemed to help cement the name in the English language.
The power of poetry. Okay, so mystery solved, name established. Let's talk about oxygen itself, O2. What is it?
Right, the common form we breathe is dioxygen, O2. Two oxygen atoms joined together. It's a gas, obviously. Colorless, odorless, tasteless.
The bond holding them together.
It's a strong covalent double bond. But here's a really neat detail about its electrons. In its most stable state, the triplet state, it has two unpaired electrons.
Unpaired electrons usually mean very reactive, right?
They often do, but in oxygen's case, this specific structure actually makes it less reactive with many organic molecules than you might expect, which is good.
Good out.
Well, it means things don't just spontaneously burst into flames all the time in the presence of air. It provides a bit of an activation barrier.
Phew. That's a relief.
Yeah.
Constant spontaneous combustion would make life tricky.
Just a bit. And this triplet state, with its unpaired electrons, gives oxygen another cool property: paramagnetism.
Meaning it's affected by magnets.
Yes. Liquid oxygen is actually attracted to strong magnetic fields. You can literally suspend a drop of pale blue liquid oxygen between the poles of a powerful magnet. It just hangs there.
Whoa. Liquid oxygen floating in a magnetic field. That's amazing.
It really is quite a sight. Then there's another form, singlet oxygen.
Singlet. What's different?
It's a higher energy state where those electrons are paired up. And this form is much, much more reactive than the triplet oxygen we usually breathe.
Where do we find singlet oxygen?
It's actually produced naturally during photosynthesis. Our immune system also uses it to attack pathogens.
But being so reactive, it could be dangerous too.
It can be. It can damage cells. That's why living things have protective molecules like carotenoids in plants to quench it, to soak up that extra energy safely.
Nature's countermeasures. What about other forms? Ozone.
Yes, ozone, O3. 3 oxygen atoms bonded together. It's an allotrope, a different structural form of the same element.
And it's famous for the ozone layer.
Exactly. High up in the stratosphere, it forms that vital layer that absorbs most of the sun's harmful ultraviolet radiation. Life on Earth depends on it.
But down here?
Down at ground level, ozone is a pollutant. Bad for breathing, a component of smog, often from car exhaust reacting with sunlight. So good up high, bad nearby.
And are there even more exotic forms?
There are. Under extreme conditions, you can get things like tetraoxygen, O4, or even clusters of O8. They're unstable, but potentially very powerful oxidizers.
Maybe for future rocket fuel.
Possibly.
Yeah.
And under incredible pressure, oxygen can even become a metal and eventually a superconductor at very low temperatures. It's incredibly versatile.
Mind-boggling. Okay, well, let's talk abundance. Where's all this oxygen? It seems to be everywhere.
No, it is. It's the most abundant element by mass in the Earth's crust. Think rocks. Minerals, they're full of oxides.
More than silicon.
By mass, yes. Silicon is number 2 in the crust. Oxygen is also the most abundant element in the biosphere, all living things, and in the oceans, because water, H2O, is mostly oxygen by mass.
And in the air.
It makes up about 21% of the air we breathe as O2. So crust, oceans, air, life, it dominates Earth's accessible environment. And it's the 3rd most abundant element in the whole universe.
Only hydrogen and helium ahead of it.
That's right. Makes up a good chunk of the sun, too. But Earth's atmosphere is really special with its high O2 level compared to, say, Mars or Venus.
And this high level is maintained. How?
Through the oxygen cycle, it's a dynamic balance.
Photosynthesis makes it.
Right. Plants on land, and especially tiny photosynthetic organisms in the ocean, phytoplankton, cyanobacteria, they take CO2 and water, use sunlight, and release O2.
And what consumes it?
Respiration, that's us and almost all other animals and many microbes breathing it in to get energy. Also, decay, decomposition, and combustion burning things uses up oxygen.
So it's this constant cycle, production and consumption.
Ideally in balance. Oxygen also dissolves in water, which is crucial for fish and other aquatic life.
And temperature matters there.
Yes, cold water holds more dissolved oxygen than warm water. That's why polar oceans are so rich in life. It's also why pollution that causes water to warm up or uses up oxygen through decay eutrophication can be so devastating for aquatic ecosystems.
It's all connected. Okay, let's zoom right into its biological role. the breath of life.
Absolutely fundamental. We touched on photosynthesis. It's the source. Those marine microbes, the phytoplankton and cyanobacteria, might be responsible for something like 70% of the oxygen produced each year. Tiny organisms having a massive planetary impact.
Using sunlight to split water, release O2, and make sugars from CO2. The simplified equation, CO2 plus H2O plus light, glucose plus O2.
Beautifully simple, profoundly important, and respiration is basically the reverse.
Glucose plus O2, CO2 plus H2O plus energy, ATP.
Exactly. We and most complex life use oxygen inside our cells in the mitochondria to efficiently extract energy from the food we eat, generating ATP, the cellular energy currency.
And how do we physically get the oxygen inside us?
Well, for us land vertebrates, it's lungs. We inhale air, oxygen diffuses across the thin lung membranes into our blood.
Where it hitches a ride.
On hemoglobin, the protein in red blood cells, hemoglobin is like a fleet of tiny oxygen delivery trucks carrying it to every tissue in the body.
What about fish? Or insects?
Fish use gills to extract dissolved oxygen from water. Insects have a system of tiny tubes called tracheae that deliver air directly to their tissues. Some invertebrates use different oxygen-carrying molecules like hemocyanin, copper-based, or hemerythrin, iron-based, but different from hemoglobin.
Life finds a way. But is oxygen needed by all complex life? I thought that was a given.
It was thought to be a given, but recently scientists discovered some multicellular animals, metazoa, living in deep-sea sediments that are completely anaerobic. They don't use oxygen at all.
No way. Complex animals without oxygen.
It shocked everyone. It shows there might be pathways to complex life we hadn't even considered. But for the vast majority of animals, oxygen is non-negotiable.
Now, using oxygen, it's not without risks, even inside us. Reactive oxygen species, free radicals.
Right. Using oxygen in metabolism inevitably produces some reactive byproducts, things like superoxide, O2, and hydrogen peroxide, H2O2. These are often called reactive oxygen species, or ROS.
And they can be damaging, cause oxidative stress.
They can be. If levels get too high, they can damage DNA, proteins, cell membranes, but they're not all bad.
Oh. They have useful roles.
Yes. Our immune cells actually generate ROS deliberately to kill invading bacteria and viruses. Plants use them in defense signaling, too, so it's a balance.
A double-edged sword, even at the cellular level. And thinking back historically, that initial rise of oxygen.
The Great Oxygenation Event, maybe 2.4 billion years ago, it was likely catastrophic for the existing life forms, which were mostly anaerobic. Oxygen was toxic to them.
So the rise of the element essential for us was a mass extinction event for earlier life.
Probably the biggest one ever. It fundamentally changed the planet and paved the way for the evolution of oxygen-breathing organisms like us.
It's staggering to think about. And the sheer quantity we breathe.
Astonishing. A resting adult inhales maybe 5 to 8 liters of air per minute and extracts oxygen from that. Over a day, that's a lot of oxygen. Globally, human consumption alone is estimated at something like 6 billion tons per year.
6 billion tons, just for humans breathing. That really highlights our dependence.
It absolutely does. And the pressure, the effective concentration, drops as it moves from the air to our lungs, to our blood, to the tissues where it's finally used.
Okay, we've talked about how essential oxygen is, but also hinted at its dangers. Let's talk about a situation where that danger became terrifyingly real, the Apollo 1 tragedy.
Yes, that's a very stark and sobering example. January 1967, a fire during a launch rehearsal on the pad.
And the crew couldn't get out. What role did oxygen play?
A critical, tragic role. The capsule atmosphere wasn't normal air. It was 100% pure oxygen, pressurized to slightly above normal atmospheric pressure.
Pure oxygen at pressure. I can see where this is going.
Exactly. In that environment, materials that might barely burn in normal air or even be considered fire-resistant can ignite incredibly easily and burn with terrifying speed and intensity.
So a small spark may be faulty wiring.
Could, and did, lead to an uncontrollable inferno almost instantly. The pure oxygen atmosphere was a major factor contributing to the rapid spread and intensity of the fire, making escape impossible.
It's a horrifying illustration of how something life-giving can become incredibly hazardous under the wrong conditions.
That duality again.
A truly tragic lesson learned about handling concentrated oxygen environments.
Okay, moving from that tragedy to more positive controlled uses. How do we make oxygen on a large scale for industry and medicine?
The main workhorse method is fractional distillation of liquefied air.
Sounds complicated. How does it work? Basically, you cool air down until it turns into a liquid. Air is mostly nitrogen and oxygen. Nitrogen boils at a slightly lower temperature than oxygen.
So you warm the liquid air up slowly.
And the nitrogen boiled off first, leaving behind liquid oxygen that's much purer. It's an efficient way to get large
Like
quantities.
any other methods.
Another common one is pressure swing adsorption, or PSA.
PSA.
Yeah, you pass air under pressure through materials called zeolites. They're like molecular sieves. They trap the nitrogen molecules, letting the oxygen pass through. Then you release the pressure, the zeolites release the nitrogen, and they're ready for another cycle.
Clever. Like a selective sponge for nitrogen.
That's a good way to think of it. There's also electrolysis of water, splitting water into hydrogen and oxygen using electricity, but that's more energy intensive, usually for smaller scale or high purity needs. And chemical oxygen generators, often used for emergency supplies.
Like on airplanes.
Exactly.
Mhm.
Those emergency masks often use a chemical reaction that produces oxygen when triggered.
Okay, so we can make lots of it. How do we store and move it?
For smaller amounts, high-pressure gas cylinders are common. You see them in hospitals, workshops.
That's whole metal tanks.
Right. For bulk transport, it's more economical to liquefy it. It takes up much less space as a very cold liquid. So
Mhm.
it's transported in large, heavily insulated cryogenic tankers.
Like big thermoses on wheels.
Pretty much, keeping it incredibly cold around minus 183 degrees Celsius.
So what's the biggest use for all this industrial oxygen?
Steel making, by far, uses more than half of all commercially produced oxygen.
Well, why does steel need oxygen?
You inject pure oxygen into molten iron in a basic oxygen furnace. It reacts with impurities, especially excess carbon, burning them off as gases. It also removes sulfur and phosphorus. It's crucial for making high-quality steel efficiently.
Okay, steel. What else?
The chemical industry is another huge user. Making ethylene oxide is a big one.
Ethylene oxide, what's that for?
It's a key building block for making plastics, like PET for bottles, and also for producing ethylene glycol, which you know as antifreeze.
Ah, right, antifreeze. Any other major uses?
Metal cutting and welding, definitely. Oxyacetylene torches burn acetylene gas with pure oxygen to get incredibly high temperatures, hot enough to cut or weld steel.
And rockets.
Oh yeah, a powerful oxidizer for rocket fuel. Liquid oxygen, or LOX, is very common in rocket propulsion, paired with fuels like kerosene or liquid hydrogen.
Okay, switching gears to medicine. Oxygen therapy seems fundamental.
Absolutely crucial. It's used for a huge range of conditions where people aren't getting enough oxygen into their blood, things like COPD, pneumonia, heart failure, asthma attacks.
How is it given to patients?
Depends on the need. Could be a simple nasal cannula, those little tubes under the nose, or various types of masks delivering higher concentrations. Older methods included oxygen tents, though they're less common now.
And what about hyperbaric oxygen, breathing oxygen under pressure?
Hyperbaric therapy, yes. Patients go inside a sealed chamber pressurized with pure oxygen. This dramatically increases the amount of oxygen dissolved in the blood.
What's that used for?
Classic uses are treating decompression sickness, the bends in divers. Also, carbon monoxide poisoning, certain types of non-healing wounds, gas gangrene infections. It forces oxygen into tissues that aren't getting enough.
Fascinating. And life support in extreme places.
Definitely. Spacesuits use pure oxygen, but at a lower pressure to allow flexibility and avoid toxicity issues. Submarines and deep-sea diving rely on carefully managed oxygen supplies, often mixed with helium or nitrogen.
We mentioned airplanes already. What about recreational uses? Oxygen bars, athletes.
Yeah, oxygen bars exist where you can breathe supposedly enriched air. Supplemental oxygen for athletes before or after exertion is also a thing. The actual health benefits for healthy people are, well, highly debated. Likely minimal, mostly placebo.
So maybe save your money on the oxygen bar. Okay, let's briefly touch on compounds. Oxygen isn't always just O2. It loves to react.
Oh, it's incredibly sociable, chemically speaking. Forms compounds oxides with almost every other element. Its usual role, its oxidation state, is nemator 2.
And the most famous oxide is?
Water, H2O. Hard to overstate its importance. The unique properties of water come from oxygen's bonds with hydrogen and the way water molecules interact through hydrogen bonding.
And in rocks and minerals.
Everywhere. Silicon dioxide, quartz sand, aluminum oxide, corundum, sapphire, ruby, iron oxides, rust, calcium carbonate, limestone, shells, complex silicates. The Earth's crust is basically a giant collection of metal and non-metal oxides.
Even the trace CO2 in the atmosphere is an oxide.
It is, and in biology, oxygen is fundamental not just for breathing, but as part of molecules. It acts as a ligand, binding to metals and proteins like hemoglobin and myoglobin.
In organic chemistry. Lice molecules.
Absolutely stuffed with oxygen. Alcohols, ethers, ketones, aldehydes, carboxylic acids, esters, sugars, fats, proteins, DNA. Oxygen atoms are key structural components in nearly all biomolecules. Many essential solvents contain oxygen too, like acetone or methanol.
So it's not just the gas, it's woven into the fabric of the planet and life itself. Okay, finally, safety. We talked about Apollo 1, but general handling.
Key thing to remember. Oxygen itself doesn't burn, but it's a powerful oxidizer. It makes other things burn much faster and hotter.
So the hazard isn't oxygen catching fire, it's oxygen making a fire much, much worse.
Exactly. Concentrated oxygen, especially liquid oxygen, LOX, requires extreme care. No sparks, no grease or oil. Those can ignite spontaneously in high oxygen concentrations. Even steel pipes can burn in pure oxygen under the right conditions.
The steel pipe's burning, wow.
Yes, and liquid oxygen soaking into organic materials like wood or asphalt can create an explosive hazard. So strict handling protocols are essential.
What about breathing too much? Oxygen toxicity.
That's a real concern, especially at elevated pressures. Breathing oxygen at partial pressures above about 0.5 atmospheres for extended periods can cause problems.
What kind of problems?
Lung damage, seizures. It can affect the central nervous system. This is a major consideration in hyperbaric therapy and deep diving with enriched air mixes. Historically, premature babies were sometimes harmed by being given too much oxygen in incubators.
So even breathing requires the right balance. Not too little, not too much.
It's all about the right concentration and pressure for the situation.
This has been an incredible journey through the world of oxygen. So wrapping it all up, what's the big takeaway?
I think it's that oxygen is just so much more than the gas we inhale. It's a fundamental shaper of our planet, from geology to the atmosphere. It's the engine of complex life as we know it.
And it's a vital tool in industry and medicine, harnessed through incredible scientific understanding.
Exactly. From Philo watching a candle under a jar, to Lavoisier's precise measurements overturning phlogiston, to understanding its quantum properties and designing rocket engines. It's an amazing scientific story.
A story of human curiosity and the power packed into this seemingly simple element.
Couldn't have said it better myself.
Well, that brings us towards the end of this particular deep dive. If you enjoyed exploring the story of oxygen with us and you want to catch more deep dives into the fascinating stories hidden all around us, definitely hit that subscribe button. You won't want to miss what we uncover next right here on Tell Me More Stories Told as Podcast.
And maybe leave you with a final thought. We've seen how oxygen is both essential for life and potentially dangerous.
Yeah.
That duality.
Right, the life giver that fueled the Apollo 1 fire.
Exactly. So think about this. What other everyday elements, things we take for granted, might hold similar, surprising, powerful dualities? Something to ponder.